Good morning. Good morning. Our next section is on statistical inference. And I have to tell you that this is probably the most widely utilized topic in statistics per se. Inferential statistics are everywhere. Now you have a handout in front of you. Statistical inference is a series of procedures in which we take sample information and we try to make sense out of it in terms of how it relates to the population from which the sample was selected. In other words, I have a sample of individuals here. I measure your heights. I can actually use inferential statistics to make a determination about how likely it is that your average height, your mean height of like 5'6", is also the mean height of all IRSC students. So we use sample information to make statements about population parameters. We essentially use sample statistics to estimate population parameters. What this is really about, as you guys will see, is decisions. We call this statistical decision making. We will be doing it for the most part the rest of the semester. Statistical decision making. And with any decision that we make, there's a likelihood that I'm correct and a likelihood I'm not correct. Especially of course with decisions where we are pretty certain about the outcome. Like if I go over to that light switch and I go like this, I am pretty highly certain that the lights are going to go off. But there's still that small likelihood that I'm wrong. There's a likelihood I'm correct and a likelihood I'm incorrect. When I go out to my car after class, pretty high likelihood that that car is going to start. I drive a Toyota, right? Pretty reliable, pretty consistent starting. Still a small chance that my car might not start. When I go into my favorite restaurant, I'm one of those guys that, I go into my, if I get a good meal somewhere, I go back and I do it again. I went into my favorite restaurant. I actually went into Duffy's last week. I like their wings. Always got really good wings. So I order wings. The three-tiered things. And lo and behold, it was terrible. They were undercooked, and had to send them back. Look at marriage. I found my soulmate. The person, look at the divorce rate. Here is a person who's highly certain that this is the right person for them, and it turns out that it's not. Decisions, the likelihood that I'm correct, the likelihood that I'm incorrect. What we're talking about is a lack of certainty. A lack of certainty, so to speak. Now I say that because populations can rarely be studied exhaustively, thoroughly, we must depend on samples as a basis for arriving at an inference concerning various characteristics of the population. Inferential statistics combines descriptive statistics, probability, logic, and common sense. Now, statistical inference actually has three main pieces. It has three pieces. The first one we call point estimation. Point estimation. Point estimation is a situation where we take some sample measurement, like a sample mean. We take some sample measurement. We automatically conclude that it's the corresponding population parameter. We simply take some sample measurement, and we automatically conclude that it's the corresponding population parameter. We can do this with any sample statistic. We can use S to estimate sigma. We can use sample variance to estimate population variance, we can use our Pearson R to estimate what? To estimate what? Rho, yeah. First day of class. So we can use any one of these sample statistics to estimate the population parameter. And that's about it. This is kind of a no-brainer. And it's such a no-brainer that if you look in your textbook, in chapter 7, they only devote about a half a page to this. That's all. And that's all the time we're going to spend on it. Things get a little bit more involved now. Inferential statistic number 2 we call interval estimation. Interval estimation. Number 3, hypothesis testing. Interval estimation and hypothesis testing. This is the stuff of chapter 8. This is the stuff of chapter 9. Now, these two inferential statistics are, a bit quite more complex because the underlying basis for these two inferential stats is a mathematical theorem that's thought to be kind of the foundation for inferential statistics as we know it. And it's called the central limit theorem. The central limit theorem. The central limit theorem is kind of it's the foundation for inferential statistics as we know it. Now actually, if you look at your notes here, I have it written down for you. And let's go over this. I'm going to read it, then I'm going to explain this to you until I'm blue in the face. You have to understand this. You have to understand this. The central limit theorem states that if an infinite amount of randomly selected samples of a fixed n are drawn from a population, regardless of the shape of the population distribution, as n increases, the distribution of sample means approaches normality, with the mean of the means equaling the population mean, and the dispersion of those means around the population mean equal to the standard error of the mean. So as you see, this central limit theorem has 3 little pieces to it. Let me explain what this means. All right. Let's suppose we take a sample. Let's suppose we take a random sample. Let's say n equals 100. We take one sample of 100 individuals and we compute a mean. Let's say that mean is 45. Whatever. We take one sample of 100 and compute a mean. Now let's say we take another sample of 100 and compute another mean. Now let's say we take a third sample of 100 and compute a third mean. And we take a fourth sample of 100 and compute a fourth mean. And we take a fifth sample and compute a fifth mean. And let's say we do this 1,000,000 times. Let's say, or an infinite amount of times. Or let's say a million times. Okay. So now we have these million samples of n equals 100 with 1,000,000 means that we've computed, right? So let's just imagine, visualize, 1,000,000 samples of 100. And so now we've computed 1,000,000 means. That's a lot of means. And just sort of, visualize all these means, all these numbers, that they're numbers that we've computed. We got this big old data set with 1,000,000 means in it, 1,000,000 numbers that we computed. Are you with me? If we were to plot a frequency distribution of all these 1,000,000 means, if we were to plot a frequency distribution of all these 1,000,000 means, the distribution would have this shape. The distribution would be relatively normal. We're familiar with this, aren't we? Yes. If I were to take all those million means and compute a mean of the means, in other words, if I were to sum all those numbers and divide by 1,000,000, the mean of those means would equal the population mean. That's the second piece of the central limit theorem. The mean of those means would equal mu, the population mean. And the dispersion of all these means around the population mean we call the standard error of the mean. The standard error of the mean. The standard error of the mean is symbolized a couple of ways: sigma subscript x bar or s subscript x bar. Sigma subscript x bar is sigma over the square root of n. S subscript x bar is s over the square root of n. Let's start over again. Just clear your mind. I threw all that at you. Let's do this again. What did I just say? I said inferential statistic number 2 and 3 get a little bit dicier. Why? Well, because the underlying basis for 2 and 3, and really the underlying basis for inferential stat as we know it, is this mathematical theorem called the central limit theorem. And just imagine, and it's written down for you here, but let me just explain it to you again. Imagine that we take an infinite amount of randomly selected samples of a fixed n, or let's say an infinite amount of samples of, say, n equals 150, thereby computing an infinite amount of means, sample means. So now we got an infinite amount of sample means, or a billion sample means, or a lot of sample means. Let's say we wanted to plot all these sample means. The distribution would be relatively normal. If I took all those sample means, that infinite amount, or those, that billion, or this really, and I computed a mean of those means, it would equal the population mean. And the dispersion of all these little means around mu, we refer to as the standard error of the mean. Now, chapter 7 is all about this. What I've just described to you, based on this central limit theorem, is what we refer to as the sampling distribution of the mean. The sampling distribution of the mean. Per the central limit theorem, an infinite amount of randomly selected samples of a fixed n, compute an infinite amount of means, plot those means. The distribution is going to be relatively normal. The mean of the means is going to equal the population mean. The dispersion of all these means we refer to as the standard error of the mean. So, class, visualize an infinite amount of normally distributed sample means. So each one of these little data points on this theoretical curve is a mean. Now, we know the characteristics of the normal distribution. We can partition this curve just like we always did into these segments, and we can draw our areas we can draw our scale of z. And we can sort of put these things together like we did before. The sampling distribution of the mean, the underlying basis for inferential statistics as we know it. This theoretical, it's a central limit theorem, this theoretical distribution of sample means, normally distributed, with the mean of the means equaling the population mean. And again, the dispersion of all these means around the population mean equal to the standard error of the mean. So, what the standard deviation was to the frequency distribution back in descriptive statistics, now the standard error of the mean is to the sampling distribution in inferential statistics. Let me repeat that. What the standard deviation was to the frequency distribution back in descriptive stats, the standard error of the mean is to the sampling distribution in inferential stats. The underlying basis for inferential statistics as we know it.
Can you repeat the last line, like the second part?
Absolutely. Okay. So I said what the standard deviation was to the frequency distribution back in descriptive stat, the standard error of the mean is to the sampling distribution in inferential statistics. Okay, now, again, this is basic concepts. We need to introduce some more basic terminology. Remember I said this stuff's a language? This is what I mean. I didn't invent this stuff, all right? We have this thing called sampling error. X bar minus mu. So you might see me refer to X bar minus mu as sampling error. Sampling error is simply the distance from any mean on the sampling distribution from mu. It's simply the distance from any mean on the sampling distribution from mu. So very simply, at this position, we wouldn't have a whole lot of sampling error, right? No. Oh, at this position, yeah, lots of sampling error, because we have lots of distance from this sample mean from mu. Sampling error is considered random and non-systematic. Sampling error is considered random and non-systematic. In other words, random, aka, continuous random variable, normally distributed, so to speak. Non-systematic means we don't know, whenever we take a sample, we really don't know where any individual sample mean is going to fall relative to mu in most cases. We don't really know where any individual sample mean is going to fall relative to mu. We have another very important concept which we'll be working with the rest of the semester, and these are all things, class, that we need to get down now. These are all basics that we have to get because we're going to be working with them the rest of the semester. Critical values. We're going to call critical values CV. The critical values. Critical values are considered cutoff points. Or perhaps thresholds. cutoff points or thresholds. There's a couple sets of critical values that we'll be working with right now. And in reality, there are tons. There are many, many, many critical values. It's all related to this. But for now, because we're just beginning, we're going to start with two sets of them. Negative and positive 1.96. Negative and positive 2.58. We're going to work with these two sets right now. I'm going to call these the 196s, and I'm going to call these the 258s. Let's go back to our sampling distribution and see what these numbers really mean. 1.96, negative 1.96. The 196s are the cutoff points which constitutes 95% of the area. The 196s are the cutoff points which constitute 95% of the area under the sampling distribution of the mean. Do I need to repeat that again? I probably should. The 196s are the cutoff points which constitute 95% of the area under the sampling distribution. So from this position, from this positive 1.96, 2.5% of the area falls from here back. 2.5% of the area falls from here back. 2.5 plus 2.5 equals 5. Added to the 95% equals just about the whole area under the curve. So think of the area from this position back this way to be about 2.5% of the area, and the area from this position back this way to be about 2.5% of the area. And actually, if you get your z-tables out in your books and you go to a positive 1.96, if you get your z-tables out in your books and you go to a positive 1.96, you will see the number 0.9750, and that's the area from here back. 0.9750 plus 2.5% is about 100%. If you go to a z of negative 1.96 in your z-tables, you're going to see the number 0.0250. That's 2.5%, isn't it? That's telling us 2.5% of the area falls from here back. 97.5% of the area per your z-table falls from here back. Of course, 2.5% falls from here to here. These areas are going to be extremely important. We need to know these. Another important set of critical values, the 258s. Negative 2.58, positive 2.58. The 258s are the cutoff points which constitutes about 99% of the area under the sampling distribution of the mean. Again, let me repeat that. The 2.58s are the cutoff points which constitutes about 99% of the area under the sampling distribution of the mean. So if you go to a positive 2.58 in your z-tables, you will see 0.999 some kind of number. About 99 point blah 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 percent of the area falls from here back. About 0.5% falls from here back. It's actually 0.0049, which is about 0.5%, round up 0.05, about 0.5%. If you go to a negative 2.58 on your z-tables. That would be the area from here back. You're going to see the number 0.0049. And that's telling us that about 0.5% of the area falls from here back. So we have about 0.5% area from here back, 0.5% area from here back, 1/2 plus 1/2 equals 1%, added to the 99% equals about 100% of the area under the sampling distribution of the mean. So again, remember, for now, memorize. 95% area falls from here to here. Therefore, 2.5 area falls from here back, right? 2.5% area falls from here back. It all totals to 100%. Around 99% area falls between the 2/5/8. Therefore, about 0.5% falls from here back area. 0.5% falls from here back. 1/2 plus 1/2 equals 1. Added to the 99% gives us about 100% of the area under the sampling distribution of the mean. These areas, very, very important. We're going to be using these areas the rest of the semester. Okay, armed now with this information, we can actually proceed to inferential statistic number 2. Which we call interval estimation. Interval estimation. This is the stuff of chapter 8. This is the stuff of chapter 8 in our textbook. You have a reading assignment. If you notice, if you've kept up on your syllabus, chapter 7 and 8, chapter 7 is all about sampling distributions. Chapter 8 is all about interval estimation. If you look at your notes, interval estimation is a situation where we take sample information, and in reality, it's usually in the form of a mean. We take sample information, and we estimate a range of potential means given this notion of repetitive sampling. When I talk about central limit theorem and that notion of an infinite amount of randomly selected samples of a fixed n, that's exactly what I'm talking about, repetitive sampling. And what we're doing with interval estimation is we're given a set of sample information, and we're going to pretend that we not only take like one sample, n equals 100, with one mean, we're going to pretend that we replicate that scenario an infinite amount of times. Gee, I wonder what the range of those potential means would be. This is what we're doing. I know it's very dry, okay? This is what we're doing. Look at chapter 8. How we make this determination is through computing what we call a confidence interval. It's abbreviated CI. The confidence interval. It actually has a formula. Write this down. CI with a little .95 underneath the I. We're going to be computing a 95% confidence interval. We'll see what that means in it. These are very common, by the way. It's actually the mean plus or minus z critical value, z subscript CV, z critical value times standard error of the mean. And we see that formula right to the right over there. The 95% confidence interval is the mean plus or minus z critical value times standard error of the mean. Let's see how this all works. It's very simple, actually. Don't complicate this stuff. Let's suppose we take a sample of 100. We randomly select a sample of 100. One sample of 100. And we compute a mean. Let's say that mean is 45. And let's say our standard deviation is 3.5. Great. We've now have one set of sample information. Now let's pretend we replicate this an infinite amount of times. Let's pretend that we not only take, we've taken one sample of 100. Let's take an infinite number of samples of 100. Gee, I wonder what the range of all those infinite amount of means will be. This is what the confidence interval does for us. Look at chapter 8. It really gets into the details. That's part of your homework. There's nothing to be turned in. I want you to read chapter 7 and 8. Let's compute this confidence interval. It actually requires the standard error of the mean. Look at the formula over there. Let's compute this really quickly. Standard error of the mean, s over the square root of n. 3.5 over the square root of 100. It's 3.5 over 10. Standard error of the mean is 0.35. Standard error of the mean, 0.35. Class. So the standard deviation of this sampling distribution with this mean of 45 is 0.35. Therefore, what does 1 z unit equal to in this case, class? 0.35. Yeah. That should come to you immediately. That should come to you immediately. Let's compute the confidence interval. The 95% confidence interval is the mean, 45, plus or minus z critical value. Look at the sampling distribution, class. We're computing a 95% confidence interval. What is our critical value going to be? 1.96 times the standard error of the mean, 0.35. Now we just work this out. We have plus and minus, therefore we're going to have two answers, right? The 95% confidence interval is the mean, 45, plus or minus. This times this is 0.69, bless you, 0.69. The 95% confidence interval is 45 minus 0.69, 44.31. 45 plus 0.69, 45.69. This is our answer. What does this mean? What does this mean? This is what this means. Interpretationally. Interpretationally, this means that given this set of sample information, there's about a 95% likelihood that if I were to replicate this an infinite amount of times, the range of potential means would be from 44.31 to 45.69. Visually, what does this mean? We're using x bar to estimate mu, aren't we? Let's put the 45 right here. And we're going out in units of what? Very good. So the 45.69 would be right where the 196 is, and the 44.31 would fall right where the negative 1.96 is. See that? So this would be 45 plus 0.35, 45.35, 45 minus 0.35, 44 point what? 0.65, and so on. The range of potential means. The range of potential means. I would like you to take a look at chapter 8.